A legal case study featuring explosive vapors, a short video featuring Dr. Kevin Linfield. This video is brought to you by Airflow Sciences Corporation for all your flow modeling and testing needs since 1975. In a recent case, Airflow Sciences provided engineering services and expert testimony regarding an explosion of a commercial vessel that resulted in 2 fatalities. Investigators determined that the explosion was caused by gasoline vapors inside the enclosed hull. Our engineering team evaluated the air exchange of the hull, showing with careful analysis that the existing hull design was inadequately vented. We also performed engineering analysis for 2 vent designs and showed how simple modifications may have prevented severe buildup of these explosive vapors under certain conditions. Our engineering services on this case included engineering handbook calculations via a spreadsheet, wind tunnel testing, and computational fluid dynamic simulations of the existing hull design, as well as 2 modified ventilation systems. Our analysis and simulation of the hull interior showed how the modified vent designs were likely to clear gasoline vapor from a hull of a moving vessel within 6 to 15 minutes, whereas the existing design was unlikely to ever do so. The animation that is about to begin shows 3 different design scenarios of the investigated vessel while it is traveling at 20 miles per hour. The image on the lower part of the screen is a 3D model of the vessel with its original as-built design. The hull of this vessel is completely enclosed except for 2 gooseneck tubes that provide the only access to outside air. These tubes are 1 9/16 inch diameter. They open downward toward the deck, and they are located on the starboard side of the vessel. The tubes do not extend very far into the hull itself. The images on the upper part of the screen show 2 potential design modifications to the hull. The vessel pictured in the upper left contains 2 6-inch diameter vents, one facing forward and one facing aft. Unlike the original as-built design, these vents do extend down into the lower part of the hull. The image in the upper right shows a similar design. However, instead of 6-inch vents, the upper right vessel features smaller 4-inch diameter vents. In this video simulation, each of the 3 hulls starts out filled with gasoline vapor, indicated by the pink color. At about 2 minutes into the simulation, we notice outside air starting to permeate the top left vent design, as seen by the green color interface between the gasoline vapor and fresh air. The forward motion of the vessel causes fresh air to enter the enclosed hull through the front vent. The resulting pressure differential causes the vapors within the hull to exit through the rear vent, eventually clearing the enclosed hull of all flammable vapor. It takes about 6 minutes for the gasoline vapors to be completely evacuated for the case with the 6-inch vent. With the 4-inch vent design on the top right, the same effect is noticeable starting at around the 6-minute mark. This smaller vent allows less fresh air to enter the hull compared to the 6-inch case. So in this design, the gasoline vapors take longer to exit the hull via the rear vent. Here again, the forward movement of the vessel causes fresh air to enter the front vent, pushing the vapors inside the enclosed space out through the rear vent and clearing the hull of gasoline vapor. With this 4-inch design, it takes about 15 minutes for the gasoline vapors in the hull to be completely evacuated. These simulations continue for an elapsed time of 15 minutes. At that point, looking at the original design on the lower half of the screen, no noticeable amount of gasoline vapor was displaced by any fresh air. This state continues indefinitely, indicating that the gooseneck tubes are doing very little to eliminate any flammable vapors that occupy the enclosed hull. The CFD simulations performed by ASC showed that ventilation could be possible in a vessel of this type with the appropriate designed vents. The as-built design was ineffective at eliminating gasoline vapors from the vessel hull. In supporting this case, Airflow Sciences produced valuable scientific reports, graphics of the design modifications, and the preceding videos that showed the simulation of vapor dispersion inside the hulls. Our senior engineer, James Paul, provided expert testimony which resulted in a favorable outcome for our client. For more information on engineering legal work and testimonies, please visit www.airflowsciences.com. Thank you, and have a wonderful day.